All right, so we are starting off with the 2024 AP Physics C Mechanics Set 1 FRQs. If I have any corrections, and these are harder tests, so I probably have some mistakes in there, but if I have any corrections, I will put as a pinned comment. So check those if you think I did something wrong. Block A and Block B of masses M and 3M are arranged in a setup consisting of an ideal spring with the spring constant K and a horizontal surface. Friction between the surface and the blocks is negligible except for the region of length D, okay? Where coefficient of kinetic friction between there is mu. So we're going to have a spring, frictionless, hit some friction. It's going to hit this string here, okay? Block A is held against the spring, compressing the distance xc. So we're going to compress it x, okay? Fair enough. At time t equals 0, block A is located at position x equals x0. So it's located there and released from rest. After the block is released, the following occurs. At time t equals t1, block A is at x equals x1 after traveling a distance xc. Okay, so that's T1. So they're putting the times here. This is T1. So I'm just scrolling back and forth. Block A moves with speed V, and the spring is the equilibrium position. So right at this point, it's moving with the speed V. Okay, at time T equals T2, after passing through distance with non-negligible friction. Okay, so this is T2 right here, which makes sense because it's called X2. Type 3, it's and it collides and sticks. So this is T3, and it collides and sticks to block B. Okay, so that's a kind of an inelastic collision there. For parts A1 to A2, express your answer in terms of M, K, D, mu, Xc, and physical constant. Derive an expression for the speed of block V at block A at time T1. Okay, so from here to here, we're just going to do conservation of energy, right? We're just going to include the spring in the system, and we're going to talk about the... Right now, at this point at x0, we only have spring potential energy, and then that's going to get converted into kinetic energy. So then we're going to say 1/2 k xc squared, that's the potential we start with, is going to get turned into 1/2 mv squared. And this is the mass of the block, mv. Okay, that's fair. And we want to solve for v here. So the 1/2s cancel, the m's cancel, and so we get the v is going to be square root of k xc squared over m. Okay, so that's that first one. Nice and roughly simple. Derive an expression for VAB, the two-block system, immediately after the collision. So we got to do two things. We got to handle the fact that it's going to lose some speed as it goes from here to here. And you can either use forces in kinematics or work in energy. And then we got to handle the collision. So there's kind of two parts to that we got to take care of. So the first part, I'm going to use work in energy. That's my personal preference for something like that when it's moving in a straight line. You could do a free body diagram, do kinematics. So the way we're going to do the work in energy is we're going to say, well, I draw a free body diagram, right? So I'm going to have mg, I'm going to have Fn, and then I'm going to have force of friction, and it's kinetic friction. And then because it's moving along this way, it's displacing this way, these two forces don't do any work, and we just have negative work done by friction because the displacement is to the right and the friction is to the left. So we would say the work done by friction is negative force of friction times the distance d, okay, which is negative mu mgd. And that's because the normal force, it's mu times the normal force because it's kinetic friction. And the normal force equals mg because there's no vertical acceleration here. And that equals the change in the kinetic energy. So that's going to be 1/2 mvf squared minus 1/2 mv squared, where this is the start of the energy we have here, right? And so that will give us the velocity of the block. So the m's can cancel here. We can multiply through by 2. You get negative 2 mu gd is equal to vf squared minus v squared. So we can add that v squared. So we get vf is equal to square root of v squared, which is this thing, k xc squared over m minus 2 mu gd. Okay, so that is that's the velocity. So that's the first part for the velocity right here. And then it's going to do, then we're going to do momentum conservation. We're going to say mvf is initially, because the 3 block, and then the final momentum is both blocks together with the mass 4m are going to move with a new velocity we'll call v, I don't know, we'll just call that v2, or well, actually we'll just call that, I should just label them v3, right, v3. Okay, so then we just set those equal to each other. Because, so we have mvf equals 4m v3. Those cancel. So then v3 is 1/4 of vf, which is really 1/4 of this thing. 1/4
square root k xc squared over m minus 2 mu gd. Okay, so that's the velocity there. Okay. On the following axis, sketch a graph of the kinetic energy of block A as a function of time from t equals 0 to time t equals t3. Okay, so we're going to gain some kinetic energy. Now, the question is about the time part. This is a little bit tricky because we're going to start with no kinetic energy, and we're going to have some kinetic energy. So as a function of time, we have to think about like what the shape of that energy graph is going to be, right? Like, is it curved up or curved downwards or anything like that? So, there's a couple of ways I'm thinking immediately off the top of my head to do this. Is because the force, if it's a function of position, it'd be a lot easier. But usually you have to think about it from, because it's a function of time, we got to think about it from a kinematics point of view. So we got to think about the forces going on here. And so, or another way to think about it is this is kind of the first part of the oscillation motion, right? We know it's going to be like a sinusoidal kind of shape. If this were stuck here and you compressed it, what would happen is, and we got rid of this, it would just oscillate. And so the shape of the velocity curve is definitely going to be some kind of sinusoid, right? Like that's one intuitive way to look at it. We could try to solve it, but you would have to solve the differential equation, and that's like kind of something. So you gotta have to understand that it's gonna be a kind of a sinusoidal shape to go from there to there, because that's what it would be. That's very similar to a horizontal mass spring. So it's gonna be kind of a sinusoidal, and it's gonna peak right here because right at the equilibrium position, it's gonna have the max kinetic energy. Oh, I'm sorry. So just to verify, that's the velocity. So this is the velocity as a function of time. Now, the kinetic energy is going to be 1/2 mv squared, right? So it's going to be 1/2 m and then sine squared of t, right? But that doesn't really matter. It's still like if you graph sine squared, it's still going to be, and you can use your calculator to graph something that's like sine squared. It's still going to be a kind of concave upward. It's going to be a kind of shape like that. So I'm trying to think if there would be an S shape to it now that I think about it. I think, yeah, actually, so it's kind of weird, but sine squared, because it always stays positive, actually has a slightly shape like this. Because sine squared, if you were to graph sine squared, it would look like this. Okay, it would look like this, but oops. But it would kind of have a zero slope right there. And then it would do something like that. I think that would be right. I'm going to double check on a calculator real quick. Yeah, I just used my calculator to graph it. So it's going to look like something like that. So anyway, that's kind of what the first shape is going to be as a function of time. Now, after we hit this point, we're just going to decelerate at a constant rate, right? So if you think about the velocity, it's going to have some initial velocity minus acceleration times time. That would be the relationship. So in terms of the kinetic energy, 1/2 mv squared, right? It's going to be proportional to v0 minus at squared. So it's going to be a quadratic. It's going to quadratically go down and then shrink to let's see. Yeah, it's going to quadratically shrink down, maybe like this. Okay? So it's going to be a concave upward. It's going to shrink down to some point there. So that's the slower part. And then from here, then it's going to move at a constant speed here at this point, right? This, because then block A, kinetic energy, because then it's not going to go any faster or slower. So using principles of work and energy justify the graph shown in part B for the time interval 0 to t1. Explicitly reference features of the shape of the graph each. Okay, so this is kind of interesting. Kinetic energy is a function of time. If you think about work, right? Work is... let me think about the principles of work and energy for this one. So if I were to make this argument, I would be talking about, well, let's look at f dx. Work is going to be the change in energy here. So we're integrating the force over the distance, but we got to do it over time. So you have to think of this as the force is m times dv dt dx. Actually, this is where you get work and energy. Let's see. Dx dt is v dv. Let me think. Easier way to think about what I would do here. This is kind of a tricky part of the question, to be honest. I'm not entirely sure. I probably would have skipped this and thought about it a little bit more. But since I'm teaching it to you guys right now, I'm just going to go with sort of my best take on what I would do at this point. The shape of the graph is we start with no kinetic energy. So the spring is going to do work, right? So think of the work is the force over the distance. So if I'm going to just talk about this, I would say like, so as initially, there's no kinetic energy. And then as the spring increases, as the block increases speed, I would say as the block increases speed, there's going to be more work done. So, okay, so maybe I'll try to balance this out, like just to make an argument. So in the beginning, the reason that the rate of change is so slow in the beginning, why does the kinetic energy grow so slowly in the beginning? It's because there's a big spring force, but it doesn't move very much in the short amount of time. So in the beginning, it doesn't move very fast. Okay, so that's why it doesn't grow very much. So as it speeds up, the force weakens. So the force is going to go down and the displacement is going to increase, right? Because it's going to move faster and faster. So there's this kind of this maximum rate at which the kinetic energy is going to be changing. Because at some point, it's going to have like kind of a faster motion in a force. And then by the end up here, the spring is not going to do very much work, right? Because the spring force is so weak. Like the F gets very, very small. So that's why there's this kind of like this S-shaped kind of curve. It's like it gets steep real here because it's applying like a medium amount of force and it's moving fast. So the displacement and the force are kind of medium. So I would probably talk about that. This is probably how I would try to word it. I would say initially F spring is large, but delta x or dx is small because the block moves slowly at a slow speed, which implies a very slow increase in kinetic energy. At the end, near T1, the spring force is small, but the block moves fast, which implies, again, small amount of work, which implies slow increase in kinetic energy. In the middle, halfway between is when it's kind of maximum. So halfway between the times, it's at a max. It has speed and some force, which implies it has the maximum work, which implies it's the steepest change in kinetic energy. Okay, so that's kind of like how that's kind of maybe what I would use as an explanation for it. There's probably other explanations. That's just what occurs to me at the very moment as I'm just thinking about it. If someone asked me, bullet in my head, figure out what you're doing. This is a tricky one to get that shape right and then to justify that shape correctly. Okay, so after the collision, the two-block system instantaneously comes to rest at times t equals 4, which occurs when the string makes a small angle with the vertical, as shown. For times t greater than t4, the system oscillates with frequency fl. The support holding the string is raised, and the procedure is repeated using a new strength of length 2l. So we're going to hit it with some energy, and it's going to oscillate, and then we're going to do it again, the same thing, but we're going to raise it. Okay, indicate the new frequency of oscillation on the two string will compare to the frequency of oscillation of the original procedure. Well, let's take a look at that. So this is the period. This is a pendulum, 2 pi root L over G, which means the frequency, which is 1 over the period, is going to be 1 over 2 pi root G over L. And so all we're saying here is everything being the same. You hit it with, it doesn't really matter the energy. All that matters is the G and the L. And if you increase it, if you double L, then the frequency is going to go down. So the F of the two L's right there. And that's because L is inversely proportional to F squared. Technically, it's not inversely proportional. Or you could say the square root of L is inversely proportional to F. And that would be probably a sufficient justification for that. Okay, that was a lot for 3 parts, and that's because this one probably took up a lot of time, and it did take up a lot of time for myself. Okay, student drops a cylinder of mass M from rest. Okay, the air exerts a drag force of F drag on the cylinder as shown. The F drag is given by this equation. Derive but do not solve a differential equation that can be used to determine the speed v of the cylinder as a function of time. Express your answers in the given quantities. Okay, so we're going to start with our free body diagram, right? mg, and then we're going to have an upward force, the drag force called bv. Now, we want to identify the acceleration. The acceleration we'll just say is downward because it's still like you dropped it from rest, so it had to start initially. And so we'll make down the positive direction. And so now we want to do F net equals ma. So downward is the positive direction, so that's mg minus bv equals ma. And then to make it a differential equation to solve for the speed, we replace a with dv dt equals m dv dt. Okay, like that. The student correctly sketches the speed v of the cylinder as a function of time. Draw a vertical line on the sketch to indicate the earliest time where the F drag on the cylinder is equal to the magnitude of the weight of the cylinder. Label this. So when you have velocity versus time, the slope definitely equals the acceleration. And we want to know when the drag equals the magnitude of the weight on the cylinder. And that means that if I think about it, if those two forces are equal, then the acceleration is 0. That means the slope of this is 0. So we'll put it right there. That's when the slope is 0 right there. So that is T1. Label this time on the time axis. So you got to label it down here. Justify the location of T1. Explicitly reference appropriate features on the sketch in figure 2. Well, let's see. So the net force is 0 when F drag equals mg. And then you have to say that implies the acceleration is 0, and thus the slope of v of t is 0. So that's when dv dt is equal to 0. Okay, I think that's enough to say that. Look, the slope is 0 there. Rather than dropping the cylinder from rest, the student throws the cylinder upward with a non-zero initial speed. Okay, throws the cylinder upward with a non-zero initial speed. The cylinder is in the same orientation as the cylinder was previously dropped. The student allows the cylinder to fall toward the ground. Indicate whether the magnitude of the cylinder's maximum downward speed after being thrown upward would be greater than, less than, or equal to the maximum speed in figure 2. After being thrown upward. Well, it's going to be equal because ultimately we're going to have mg is equal to bv still. Because if you're the maximum downward speed after being thrown upward would be the same. Well, the maximum speed, the max occurs when a is 0, right? That's what we said here. And that occurs when these two forces are equal. V is equal to mg over b, and none of those are going to change. So it's equal to. So the mass g and b are constant, right? So that would be my justification there. The student conducts an experiment to better understand the relationship between maximum speed Vmax and mass. The student collects data to determine the maximum speed for cylinders dropped from rest, each with the same physical size and shape but different mass m. The student, Vmax and mass. Okay, got it. The student graphs Vmax squared as a function of mass. Draw the best fit line for the data. Okay, so draw a line. I don't know. If you have a straight edge, this is a lot easier. It's hard to do on the computer with the OneNote. Use the best fit line to calculate experimental value for B. So remember what our relationship was is, Vmax is equal to, mg over b. So why did we do square? That's kind of interesting. Oh, I'm sorry. I'm messing up. They said BV squared, right? Oh, shoot. Sorry about that. Okay, so I caught myself. Is when Vmax squared, or so Vmax squared is equal to mg over b. So sorry about that. I messed that up. But you guys are probably yelling at me this whole time. So Vmax squared is equal to mg over b. Okay, woo. Okay, that makes more sense. So this is our y value. So this is our x value, because that's on our x-axis. So that means our slope is equal to g over b. And so we want to pick 2 points on this line that are easy to read off the graph. I'm going to pick this point. This is 0.525, and the y value is 9. And then we'll pick, say, this point right here, which is 0.1, and the y value is 2.5. Right? So then we're going to have 9 minus 2.5 over 0.525 minus 0.1 equals 9.8 over b, and then you just solve for b here. Right? So we're going to do 9.8 times divided by 9 minus 2.5, and then I get 0.641, I think. And should I have units for this thing? I don't really want to put units. What is it? Newtons per meter squared per second squared. Okay, we'll just put that. I don't know. Newtons per meter squared times second squared, or something like that, right? Because F was equal to BV squared. So B is, the way I did that is just, it's F over V squared. This is newtons, is meters per second squared. So I just flipped that. Okay. Student claims that the magnitude of the maximum speed drop from rest depends on the length of the cylinder. Student design experiment collect data that can be used to provide evidence to support the claim. Student has access but does not have use to the following equipment. But does not have to use all of the following equipment. Okay, cylinders same known length with different known masses. Cylinders in the known mass with different known lengths. A motion detecting measure velocity is a function of time. Indicate 2 quantities graph that can be used to determine whether the length of the cylinder affects maximum speed. Well, we're going to do Vmax. You don't know if the length is linear or not, and then just measure length. I don't length, I guess. Length and Vmax. Briefly now, the quantities could be used to determine the relationship between them. Now, this is not a linear relationship because you have no idea whether the length is going to affect it, like how it's going to affect it. So there's no way to know this. So you would just say that if the graph has any upward or downward trend, then there is a relationship. I don't know. It's weird that they told you this. Did they not want you to use? Did they not want to act? They didn't actually ask you to design it or say anything about it. They just told that to you. A little bit weird, but they didn't ask me to do anything with it, right? So, yeah, okay. Their downward trend, then there's a relationship. If the graph is mostly horizontal, then there is no relationship. Okay, so, okay, cool. Number 3, uniform rod length L, mass attached to a pivot on a vertical pole shown in figure 1. There's a non-negligible friction between the rod and the pivot. Oh, okay, so there's between the rod. Ooh, okay, so there's some friction here, some torque that's going to happen on this pivot. That's what they're telling you. A little bit interesting. We don't normally deal with torque on the pivot, but okay. Horizontal string connects point P and Q. Connects point Q to the rod to the pole. Okay, that's that string there. The rod makes an angle theta with the pole. A block of mass 3m hangs from the rod at point P. The center of the mass of the rod is located at point C. Draw label forces that are exerted on the rod. Each force must represent a distinct arrow. Okay, so you could either call this guy tension or 3m. I don't know if it's rotating, so I'm just going to call this one tension for now. Normally, I would say just put 3mg here, but I don't know that it is hangs. There's non-negligible friction. I don't know. Like, I don't know if we're going to be accelerating this thing down or not. I think it's just hanging there. I bet you could get away with 3 mg if you want to put there. I'm just gonna put that there. So we'll call this T1. This is gonna be what is the mass? It's mg, and then we're gonna have this here, tension. Now at this point, you're gonna have some kind of axial force. There's got to be some horizontal. If it's just hanging out here, there's gonna be some horizontal force to compensate this, and an upward force to counteract these things. So it's gonna be force from the axle up here, something like that. Okay. Or from the pivot. You could write that as pivot and so that would be, we'll call this T2, and that's it. Nothing else is touching it. So that's the whole free body diagram. In figure 1, point P is located 3/8 L from the pivot. Point Q is located 6/8 L. Derive an equation for the tension in the horizontal string in terms of L, M. Yeah, I think it's just hanging there. There's negligible friction. Actually, sorry, negligible friction. I don't know why I said no. There's no friction. There's no torque here. The rod makes an angle. He hangs. I think we're gonna assume that it's not actually moving. I don't know. It doesn't technically say, but I'm gonna assume that this rope doesn't break. And so what I'm gonna change this, and I'm just gonna say this is 3 mg. Because then this thing's not accelerating, so the tension here equals 3 mg, so it's fine. And that way I can just call this FT like they want me to. Okay, so what are we gonna do here? We're gonna draw our axis of rotation. We're gonna do net force equals ma, and we're gonna do net torque equals I alpha. In this case, we're gonna use the axis rotation for the pivot. 1, that's the natural point. 2, I don't need to figure out what the axial force is if I do net torque. So I'm gonna do net torque equals 0. And we'll say counterclockwise is the positive direction, and clockwise is the negative direction. Okay, so then first vector, I draw my r vector from here to here, and this is 3/8 L. But it's not perpendicular. I only need the component perpendicular, so I need to decompose this into x and y components. So I'm going to decompose it with, and then just to get the angles right, this is theta. So if this is theta, then this angle is actually theta, right? Because that means this angle is theta right here. So you got to be careful. Your theta is like this one here. So this is going to be, this distance here is going to be 3/8 L sine theta. Okay, so then when we do that torque from this guy, this component of the r is perpendicular to that, and that's going to be a negative torque, 3/8 L sine theta. Okay, and then this one, this force for this torque, this is L over 2, or 1/2 L, right? And then that's going to be, again, a similar thing. You're going to use sine theta, because this is theta. You're going to do sine theta component, because that's the component that's perpendicular to mg. So it's going to be minus mg times 1/2 L sine theta. And then you got to do the r vector to this guy right here, which is 6/8 L, or 3/4 L. I don't know why I said 6/8, 3/4 L is the way I would write that. And now this one you have to be careful of, because I don't care about I don't care about this part here. This part is going to be the sine theta. I want this part, this is theta here. I want this component which is perpendicular to the tension force, right? So this is 3/4 L cosine theta. So then that's a positive torque, because rotating this way would cause the thing to rotate counterclockwise. So it's going to be plus 3/4 L cosine theta times ft. And that has to equal 0. So now we can solve for, okay, so the L's will cancel. And then you're going to move this start over. So this is 9/8. Oh, let me just use a calculator. 9 divided by 8 plus 1 divided by 2. That's going to be 13/8. So this is minus 13/8. Mg sine theta is equal to 3/4 cosine theta times ft. So then I can solve for ft here. It's going to be, plus this is equal to 0. So move that to the other side and then divide by that. So negative, that 13/8 divided by 3/4. I get 13/6. And then it's going to be it's going to be mg sine theta, and then divided by cosine theta. Hopefully I did that right. I'm going to just check my math real quick. Do 13/8 times 4/3. That makes it 2. Sorry. Oh, yeah, that's where I get the 13/6. Okay, I use my calculator, but I always like to double check, make sure I did that math right. Okay, and then the mg stays on the numerator, and then the units of this is in forces, because it's mg and then sine over cosine. Those are dimensionless, so okay. I think I did that right. But you guys will correct me if I did that wrong. Original string is replaced with a longer string connects point Q at a higher location on the vertical pole. The angle theta remains the same. How does the new tension compare with the original tension for part B? And justify your reasoning. Well, let's see here. So what we ultimately found, and let's just look at the original free body diagram of these forces here. What we originally found is that in order for the torque to be here, we do need this component. Well, okay, let's just see if the torque is any better. So ultimately, what you have is you need the torque from this guy to balance out these two torques. These two torques are not changing, right? Those two torques stay the same. So it's really the torque from this guy. So how has the torque changed in terms of the tension? Well, they're more perpendicular to each other now, because now the force acts this way. It's more at a right angle. So this angle, like, that I have to decompose into is I don't need to do the horizontal component. It needs to be more perpendicular. Like it's more perpendicular by doing it this way, because originally it was like this, which means I only could care about this component. But now that it's more perpendicular, it's going to have a greater torque there. So what's going to happen then is you don't need as much tension in order for that torque to be. So the Ft is going to be smaller. How does the new tension, Ft new, is less than Ft? Because the rope, the string, is more perpendicular to the length from the axis. So a smaller force, smaller Ft, is needed for the same torque. Okay, that's what I do there. All right. Let's see. A non-uniform rod is now attached to the pivot. There's negligible friction between the non-uniform rod and the pivot. So non-uniform rod. The rod is a length of 1.2 meters, linear mass density this, where x is the distance from the pivot. Calculate the mass of the rod. Okay, so total mass of the rod is going to be the integral of just dm, which is the integral of the linear density times dx, right? Because you're going to chop this thing up into little pieces at location x, and then the length of those are dx. Dx is the length times the linear mass density, gives you the mass of that piece, and then you're going to integrate this from, I guess, 0 to 1.2. So we're going to integrate from 0 to 1.2 of a plus bx. So that's 6 plus 10x dx. And so that's 6x plus 5x squared. You could just use your calculator for this. You actually do not need to do the actual integration, I don't think. And that's going to be 14.4 kilograms. Calculate the rotational inertia. This is the integral of r squared dm. Now, for the same piece here, what's the r? The r from the axis of rotation, from the pivot, the distance is just x. So then this is just going to be x squared dm, and dm we replace with lambda dx. So that's going to be the integral from 0 to 1.2 x squared times 6 plus 10x dx. Or that's the integral of 0 to 1.2, 6x squared plus 10x cubed. And again, if you guys taking calculus, you can use your calculator to do that integral. I'm just going to do it by hand. 2x cubed plus 10x to the 4th over 4 from 0 to 1.2. Just because pulling up the calculator, me typing it in, is probably going to take a little bit longer than me just doing this. But if I make a mistake, you guys will let me know. And that is 8.64 kilogram meter squared, like that. And that is the end of the exam.